Hello and welcome. It's great to see everyone out in the crowd. We have a very, very exciting session of talks scheduled here. My name is Matthew Hughes. I use any pronouns, so any of he, they, or she all apply to me equally well. Our first talk today at this session is going to be from Jonas, who's speaking on bridging Python and Apache Iceberg, the power of PyIceberg. Please welcome Jonas to the stage.
Hi, everyone. Today I'm very glad to talk about something interesting about the big data storage layer, specifically the Apache Iceberg and its Python implementation, which we call that PyIceberg. Apache Iceberg, in short, is an open table format for data management at large scale. And you may wonder, what is the open table format? And why does that matter for data management? And don't worry, you will find the answers to those questions in the next 30 minutes. And before we get started, I just want to do some quick self-introduction. I'm Jonas. I work as a software engineer at Snowflake. I'm also the PMC member of Apache Iceberg community. I'm an active open source contributor and very excited about that. So let's start from the simple Python data workflow. So first, since we are talking about data, data must be stored in some places and in some formats. The most common formats we will see is we store our data in CSV. We have defined some columns, and we have rows with values for each columns. And some more advanced format would be like Parquet or Orc, which are column-oriented, but they still store the same similar relational data. And when it comes to the data processing, we will usually, in the Python world, use tools like Pandas, PyArrow, Polars to load the data files into in-memory data frames. And so it could allow us to make operations like queries, transformations, or we can input those into any data visualizing tools to make some good dashboards. So things works very well till now. But some problems may emerge when our data set gets larger and larger. So in real case, it usually is that your data set may consist not only just one data file, but multiple. And as your data pipelines keep running, more and more files will come in. And it's usual that maybe at some point you will feel it needs to change your column name, to rename your column somehow, to promote the data type of your column from, for example, integer to long. But this will cause some column definition mismatch across your old data files and new data files. And now this usually becomes a burden on the client side, so you have to either rely on the tools to automatically merge the schema, but that's sort of error-prone, and sometimes you have to fix it by yourself. And also, existing data frame tools does not offer you any guarantees on multi-writer mode. So if you have two processes trying to update your data set at the same time, there's no guarantee which will come in first and whether you will end up with some corrupted data sets. And finally, it's usual in your large data set, we want to do some optimization during the query. For example, if my query button only cares about the data in a particular day, then it makes sense for me to manually partition my data based on the date, so that whenever I want to query my data sets using the query pattern, I should only look at the particular data file that contains all the data of that date without looking at all the data files. Now, the question becomes, all these things needs to be resolved, and now we seem to want a standardized way to resolve that. The ideal solution is that, how about we resolve that at the storage layer? So here comes the Apache Iceberg, which serves as an open table format that defines the table as a metadata plus data layer. So instead of just having a bunch of data files in your table, it adds some metadata to keep track of things like a schema, partition spec. And with this metadata layer, it will enable features like schema evolution. So now you can update your column name. You can remove, add new columns. You can promote your column types without worrying about the correctness. And it also offers you the optimistic concurrency for a multi-writer case. And now you can feel safe to put your data pipeline in like a multi-writer setup. And it also offers built-in partition and partition evolution. And it also offers very convenient functionalities like time travel queries to allow you to query your table at a previous point. Now, a little bit more about the partitioning supported in Iceberg. So Iceberg allows you to specify a partition strategy to partition your data based on the value of one or more columns. So in this slide, I showed a very simple example to partition my data based on the date. So all the rows with different date value will go into different files. For example, if my date is January the 1st, it should go into the first parquet, and if the date is May the 18th, it should go into the second parquet. This is a simple partition. And Iceberg also supports a more advanced partition strategy called hidden partitioning, meaning that you do not necessarily have to use the whole value of your column to do the partitioning. For example, if I have a column which contains a timestamp value, like I have year, month, day, and also the time, but I only want to partition my table based on the year. So Iceberg will allow you to specify a year transform in the partition strategy. So it will automatically extract the year part of the column when it decides which partition it should go. Now we have an overview of the main features of Iceberg. So let's go over the structure of the Iceberg. You will find the picture on the right-hand side may be a little bit complicated, but it will basically just contain like three major parts. The first is the catalog, and then a metadata layer, and inside you will find three different kind of metadata files, and then we have our data layers. I will go over the definition of them one by one. So first, from the bottom, we have data files. So data files are just the normal files that actually stores the data. So Iceberg supports you to store your data in the format of Avro, which is a row-oriented format. It also supports you to store data in the format of Parquet and Orc, which are more column-oriented. And of course, like Parquet is now the most popular one, and also it's the most used one across the Iceberg world. And upper one level, we enter the metadata layer. And first file we encounter is a manifest file. So manifest file is just a collection of some data files, and it will record some metadata of the data files. The metadata will include the partition data, the partition of that data file, the min-max value of each column in that data file, and the null counts and some other stats. So these stats will be helpful during the query planning so that we could make optimization to pruning data files that are not needed in operation. Upper one level, we have a manifest list. So a manifest list contains a group of manifest files that make up a snapshot of the table. And each manifest list stores the metadata about the manifest, like its partition stats and data file counts. And similarly, it is also used to prune unnecessary files during an operation at the querying planning stage. And then upper one level, we have metadata file. So each metadata file represents a table state. All the changes to the table state will create a new metadata file and replace the old metadata using an atomic swap. The table metadata file tracks the table schema, the partition config, some custom properties, and all snapshots of the table. And finally, on the top, we have a catalog, which is a server or a service that's responsible for managing and tracking Iceberg tables, pointing to the current metadata file that represents the table's current status. And the catalog is also responsible for ensuring that all the updates to the table's metadata location is atomic, so we can have optimistic concurrency in the multi-writer case. So now we've covered the features of Iceberg and its structure. The structure does not seem like very easy. It's a little bit like complicated. So Iceberg cannot like just give you like the spec and ask you to implement all of this. So the true power of Iceberg is that we have a very well-defined REPL to handle all the logic for you within SDK. So Iceberg starts its implementation in Java, but now it extends to Python, C++, Rust, and Go. And today, since we are at the PyCon, I'm going to introduce you the Python implementation of Iceberg, which we call that PyIceberg. The PyIceberg is a pure Python implementation of Iceberg APIs. It does not require any JVM in the background. Apart from Iceberg APIs, it also serves as lightweighted query engines that allow you to read the table, update your table, adding some data, and make changes. It also serves as a client tool that allows you to grab information of your catalog, of your namespace, your table. And PyIceberg provides supports for different catalog backends. For example, it can support AWS Glue, AWS DynamoDB, Hive Metastore, any SQL database, and all the other catalog server implementations that respect the Iceberg's OpenAPI catalog spec. And in the storage layer, it supports writing your Iceberg to object storage like ADLS, GCS, S3, and file system like HDFS. And of course, it supports all the main Iceberg features. Now, let's take a look at some example of PyIceberg, and you will see how easily you can use PyIceberg to create and interact with Iceberg tables. So this is a very simple code snippet if you want to create an Iceberg table. Just like in the database, when you want to create a table, you call create table and giving it a name and the definition of the table. So similarly here, now I want to create a table with 2 columns, city and inhabitants. So I first, using PyIceberg's API to define the schema, and from the top to bottom, I specify the first column to be the city with data type string. The second column would be inhabitants with a data type integer. And I also mark the city as the identifier field, which is a similar concept known as a primary key in the database. And finally, I can just use the create table API by giving it a table name and a schema. And PyIceberg will handle the rest of the thing in the background. Now I have a table. How can I add data to it? It's also very simple, just through the single API called table.append. So I first define, in this example, I define a very short PyArrow data frame with some records based on the schema just defining the last slides. And I just call table.append and give it this PyArrow data frame. And the PyIceberg in the background will generate, will first write these things into Parquet, will generate all the metadata files needed, and the table will be updated. And PyIceberg also supports other DMLs like overwrite. So you can overwrite the one record of the table by specifying an override filter. So for example, here I want to replace the row with city equals to Paris with a new record that of city equals to New York. So I can easily do that by just specifying the override filter as shown in the example. And PyIceberg also supports upsert, meaning that you could specify a data frame and if the primary key already exists in the table, then the other rows will be updated. And if the primary key does not exist in the table, the row will be inserted to the table. And reading a table is also very easy. It's through the table.scan API. So in the table.scan, you can specify row filters when reading, and you can also query the only first 2 rows and select only 2 fields, and then you can convert the scan to either a pandas data frame or Arrow or some like other library that connected supported by the PyIceberg. Now, in all those examples we just covered, you will see like all the interactions, either you write a table or you read a table, is just a single line. But what actually happens in the background, how PyIceberg utilizes the Iceberg structures to optimize the read query, how to generate all those data files, and we will see one by one. We'll start with the reading tables with PyIceberg. I will explain you how PyIceberg utilizes Iceberg structures to do file pruning and optimize the query. So now suppose I have a query that specifies the filter to be, I want ID smaller than 5 and year greater than 2021. So the first thing PyIceberg will do is to grab the latest metadata file from the catalog, and from the metadata, it will also grab the latest snapshot. And then for the snapshot, it will be pointed to a manifest list. So it will open the manifest list, and it will find that, hey, for example, I have 3 manifest file, A, B, C, and there are some metadata corresponding to that. In this case, for example, it contains stats like all the data in manifest A will have ID from 1 to 10. All the data in manifest B will have ID 4 to 15. And similarly, in the C, all the ID will be ranging from 10 to 20. And since my query specifies I only want ID smaller than 5, so in the result, I only need to look at manifest A and B. I don't need to look at C in my planning. So this is the first part of the optimization that we can pruning out the files that are not needed. And once we have all the manifests we need to look into, we will look at each manifest, and we will find that in each manifest, we will see a list of all the data files. For example, in one manifest, I can have A and B, and each data file will also have some stats corresponding with it. For example, in A, it specifies that all the data in that will have ID equals to 1 and year ranging from 2001 to 2020. In data file B, it may say its ID equals to 2 and year ranging from 2020 to 2025. Since the filter specifies that I only want year greater than 2021, so PyIceberg will decide, hey, I only want the data file B. I don't have to read into or look into data file A anymore. And once we finally pruning all the unnecessary files, and we have a list of all the data files that's needed to be read during this query, we will send these files to the PyArrow, and we will use PyArrow to actually read the Parquet files and apply the filters, and finally convert that to either a PyArrow data frame, PyArrow record batch, or a Pandas data frame. So that is the read path, and now we are going to look into the write path. So during the read, we go over the structure from the top to bottom. We start from the metadata, and we end up in the data layer. And now, in the write, it's just the reverse. We will start from the bottom. We will first write the data files, and we will generate the metadata files up to the top. So for example, let's say I just want to append a PyArrow data frame to the Iceberg table. The first step would, of course, to use PyArrow to write the data frame into a set of the Parquet files, which we call the data files. And then upper one level, we will group all the data files into a new manifest. And remember, we will need to record the stats for each data file. And once we have the new manifest, then we will need to construct a new snapshot, because now we are adding data to the table. The new manifest will definitely have to be in the new snapshot, but all the existing manifests have also to be in the snapshot because we are not deleting anyone. So the new manifest list will consist of manifest A, B, C, which are the previous one, and the new manifest, and corresponding with their stats. Finally, we are going to generate the metadata file, which includes the new snapshots, and we will ask the catalog to do an atomic swap to point the current metadata pointer to the new metadata. And now the table update is considered completed. Okay, so we've covered how PyIceberg basically process the update, table update, and table read. So now let's take a look at more features supported by the PyIceberg. So first would be a very useful one of the schema evolution. as I mentioned, Iceberg will allow you to update your column name, add any column, remove any column at any time. So PyIceberg will also support that through the API called update schema. It's very simple. You just call the update schema in a context manager, and you can use intuitive API name like add columns, rename column, delete column, or update the column's data type. And all this will be metadata-only operations that does not involve any data rewrite. Similarly, PyIceberg also allows you to update your partition strategy at any time with a similar setup than as the schema evolution. You can call update spec API, and you can add a partition field, you can remove a partition field, or you can rename a partition field. And all this will be metadata-only update. All your existing data files will remain in their partitions at the time they are added to the table. Only the new data added to the table after this partition strategy update will respect this new partition strategy. This will eliminate the need of rewriting your whole table if you just want to change your partition strategy. And also, since I keep mentioning that PyIceberg supports the optimistic concurrency, so it also provides like a transaction semantic to offer you the table-level transaction. The transaction in PyIceberg means that you can combine multiple table updates in one. And so, for example, here, I start a transaction, and within the transaction, I first add a column to my table. I then do a data override, and then I set some properties. And all these three table updates will be committed as a whole. So if, like, for example, the override fails in the middle, then all the updates will be abandoned. So my schema won't be like updated. So this will be very convenient when we want to ensure the consistency across like multiple table updates. Finally, just want to final technical part. I just want to give you an example of the time travel query. So the time travel query means that you could query a table at a previous state. So what does that actually looks like? First, in this example, I first append arrow table 1 to the table. I recall some timestamp. And then I override the whole table to arrow table 2. So, but now, let's say if I want to query my table at the stage before the override happens, what I should do? I should use the snapshot as of timestamp API. So I give it a snapshot. I give it a timestamp, and this API will return me the closest snapshot before that timestamp. So I got the previous snapshot, and during the table read, I just give it the snapshot ID, and the table read will be held against the table at that previous stage. Okay, so today I've covered a lot about the PyIceberg basics and also how PyIceberg can allows you to interact with Iceberg tables. But PyIceberg does not only limit your interaction with Iceberg in the Python world. And in fact, any tables that are written or updated by PyIceberg could be accessed by other query engines. For example, open source one like Apache Iceberg, Apache Flink, Trino, and commercial one like Snowflake. And also, please note, like those engines does not necessarily have to be like in Python, and in fact, most of them are in Java. So this Iceberg's true power, it offers you a unified storage layer across tools, enabling open and flexible and scalable data workflows. So in other words, like as long as like your tools can read and write based on the Iceberg spec, it will allows you to. It will provide you the full capability of that tool, and you can choose whatever the tools that most fits your need without worrying about that you have to duplicate your data at some place or do any data migration. Yeah, and some useful resources if you are interested in learning more about Iceberg or PyIceberg, please go to the links above. They are the official websites of the Iceberg and PyIceberg. And I've also provided a workshop that's written in Google Colab. And if you can find my slides somewhere in the PyCon website, you can access to that. And it will give you some hands-on experiences on utilizing PyIceberg to interact with Iceberg tables. Yeah, and that will be everything I want to cover today. Thanks for coming. And so it seems we have 2 minutes for the Q&A sessions, so I will just answer any questions.
Yeah, thank you for the talk. With the, to me, Iceberg looks, with the exception of tighter integration with PyArrow, it looks exactly the same as Delta tables. Could you explain the difference and why an organization would choose Iceberg over Delta?
That's really a good question. So the question actually is a current very popular one about how you choose whether you should choose Delta or whether you choose Iceberg. And I would say that really depends on your organizational needs. I would recommend so. Personally, from my stance, I would recommend Iceberg more because of its community is more diverse, so more it's involves more companies and the community is more active. So yeah, but in general, I would say there's no straight answer to hey, you should definitely choose Iceberg or you should definitely choose Delta. It's just based on whether you view the interoperability of the Iceberg, whether you want to integrate that with more tools, and you can make the decision based on your actual needs.
Can you use something other than timestamps for a snapshot, like a version number?
You mean during the time travel query?
Yeah, for the time travel query.
Yeah, that's really a nice feature that we want to put into the community. So, for example, in the Spark integration, it will have the SQL semantic building for the time travel. It's just select star from the table as of timestamp 1. And so PyIceberg, currently, it supports the basic ability to do the time travel, and it's of course makes sense to build an upper layer API to be more convenient. Okay. So
Please join me in thanking Jonas again for this wonderful presentation.